Alright guys, get a book. And we're going to get through this chapter and half of the next one. And we'll have a plan, guys. If we cover the circuit stuff online, if we cover the circuit stuff online, we'll be done in about 2.5 weeks and review from there on. So we'll have about 3 or 4, we'll have about 4 weeks to review. Okay? But we're doing okay. Alright. Guys, chapter 20, what was it? 27, 28. We'll finish that one and get into the next one. And what we'll have left to cover here, that's about it. We've done everything that we want to do. Okay, go to the next chapter. Chapter 29 and page 884. The I just follow my notes. And on this stuff, guys, do not get bogged down and look at and say, this is just too weird, too hard. It's not. Make sure you get the conceptual first and the math will follow, okay? Here we go. All right.
Anybody got 10? I mean, 10 something.
Okay, guys, we're going to do magnetic field due to a moving charge. The fact that the charge is moving, it produces a magnetic field, okay? If it doesn't move, you don't have a magnetic field, all right? All right, here's the equation for that. Mu sub O. There you go. I can't stop in the middle of lecture. I just can't. Time's too precious. Sorry. Okay. Okay. There's the mathematical definition. Just write it down, then we'll go over it. Okay. Ira, come here, would you?
I'll play over there. Yeah, I'm really those are gonna be like this.
I'm too taken away from that.
All right. Someone use the S word while I was in there. Where did the S word? S-H and so on.
Oh, that's not an answer.
No.
The answer?
Oh, what?
I say shut up, and I can get that. All right, guys. Now here's the deal. Let's write out what all this garbage means, and then we'll get the direction. This is how much the magnetic field is. It just doesn't tell you what direction it is, right? Well, right hand rule will get that to you. It's kind of weird, but it's not hard. Okay. B is just.
You're just not going to have it.
This is that, right? I'm not going to rewrite the whole dumb thing, but it is in Newton's. Oh, I'm sorry, it's Tesla's. That's the units for it. And let's see, y'all know mu sub Q is just your moving charge. Well, everything up there, you know. Do I need to, the only thing you might not know is that thing right there. What does that mean, by the way?
What's the little ammo?
Yeah, what's mu sub O?
What are those stupid things, you know?
It's just,
I hate when it doesn't on stuff.
No.
it doesn't know. I don't know, I've never seen the little know, and I've been coming every day.
All right, here we go, guys. This means,
Make sure the M and E.
let me write this for you.
Guys.
Here you go. Let's say, let me draw you a picture here. Here's your moving charge this way. It's possible, whatever, it's going that way, that's your view. And you want to find the B field due to that thing at this point right here, okay? Okay. And so therefore, R would be from, this is R right here. But you don't need all of R. That's R, right? You need the unit vector R. In other words, it's the direction of R, but it's only 1 unit long. So it doesn't change the amount in this equation. You follow me? But it does give you the right-hand rule thing, is why it's there. So, you know, the unit vector is going to be just this thing right here. That's what that means right there. It's 1 unit long in the direction of R.
Oh, just 1 unit long.
Yeah. It doesn't change the amount, though, it does. It's times 1.
So how would you know what a unit?
We don't care. I mean, well, ask your question, then I'll answer it. Ask it.
Like how long is a unit?
Oh, it's 1 unit. In other words, if this is distance, it's 1 meter.
Wait.
It's 1 unit. Whatever is a unit, it's 1 unit long.
Oh, it's always gonna be 1?
Yes.
Whatever the unit is.
That's why. Yes. Whatever are dimensions of the actual thing, it's one of
Why does it
those.
matter if it's up there, if it's not gonna make
It gives you the direction.
It just helps with it has to do with the right-hand rule. It's why it's there. Okay. But anyway, so that's what that's about. And obviously, this thing can be written another way. And let's write that. So everything else you know here, that's what I'm not going to write. R is just going to be.
What is mu sub O in this case?
Mu sub O, haven't had that before?
No.
We only have east of them.
Okay, mu sub O, 8.85 times 10 to the negative 12.
Wait.
It's right there.
Oh, is that E sub O?
That is E sub O.
Yeah. Mu sub O, it's different. It's different.
4 pi.
There you go. 4 pi times 10 to the minus 7.
4
4 pi times 10 to the minus 7. Tesla meters per amps.
Tesla meter
Minus
per
7?
Yeah. 4 pi
4, 5.
times 10 to the minus 7 Tesla meters per amps.
Tesla per
Tesla
meter
meters per
newton.
gas.
What?
Comes up with
I didn't know Tesla meters were newtons.
No, it's
What?
Tesla meters are newtons. Like Tesla times
We went over
meter
it,
equals
yeah.
1 newton.
Are you serious?
Did we?
That's what it said.
No, like, I mean,
That's crazy.
The 10.
Tesla meters per amp.
Oh, you were here, Dave?
Tesla meters per amp. No, all of them.
Okay, is everybody good? Other than that, everything else should look familiar to you. But you can write it another way, and that is the amount without the vectors, and that's this. V equals mu sub O 4 pi times Q times V over R squared, right? Times what? Because anytime you see a cross product, it's times sine of theta. Everybody good? Where theta is the angle between what?
The radius and the.
V and R. V unit vector. In this case, this is theta right here. Okay.
So. Never mind.
Is that not weird? A moving charge produces a B field?
Moving charge is the B field.
That's what that says. A moving charge produces. Because if V is 0, there's no B field produced by it, right? Everybody clear? Now, 2 things I want to do about this. One is, well, the amount, the sine of theta. So, if this thing is moving that way, where's the B field the greatest? In general.
It's directly above us.
Either it's on this line here, right?
Yeah.
Because theta is going to be 9 degrees, sine 9 is 1, correct? In other words, at a certain radius, anywhere apart from that, you get less, don't you? And if you're right directly in front of the thing, the B field's 0, isn't it, due to that moving charge? And if you're behind it, it's 0, right? Because it's 180.
Yeah.
Oh, yeah, it is 180. Because V is that way, little r's that way. Follow?
So, just on that line, it's gonna be the strongest.
Yes, at the same rate as anywhere else, you know what I mean? Because the closer you get to this thing, the greater it is. All right? Next thing I want to say is this. Okay, now let's get the direction. So let's say we're going this way, and we want to get the direction of the B field at that point due to this charge moving. Okay, it's the right hand. All you do is, and this is weird, because usually what you're doing, you're up here. Well, no, now you're down here because you're getting the B field at that point, aren't you? So put your fingers at the direction of V, which is that way, right? Curl your fingers towards little r. Little r is that way, so curl down. The B field's into the page. Is that not weird? The B field, this moving charge at that point is into the page. In other words, you're going from south to north into the page, right? Makes sense?
When it starts moving.
Huh?
When it starts moving, that's when
Yeah, it has to be moving though to reach the B field. A charge sitting still doesn't really, you know, hey, this is what's weird.
So what would happen if it was an identical charge moving in the opposite direction underneath?
Well, I was just fixing to think about that kind of stuff. Here's what I was thinking. It's similar. Yours is another step in the process. What I was thinking was this. Okay, let's say the charge is at rest relative to one person. But let's say another person is moving relative to this, the charge that's rest. There's a magnetic field in that person's frame of reference from that charge that is at rest in another frame. You follow me?
Really relative.
What I'm telling you now has nothing to lessen. I'm just thinking along the line of logic, okay? Yeah, so you can forget this. But in other words, so let's say the charge is at rest. There's no B field, okay, if I'm at rest relative to the charge, right? But if I'm moving this way relative to the charge, and the charge is not at rest relative to me, is it? So in other words, if I'm moving in the charge rest, there's the B field by that charge where I'm at. That's weird.
That's crazy.
But you follow me?
Yeah, so it's not moving
because you're moving, but it's not moving.
But the main thing is, if a charge is at rest relative to you, there's no B field relative to you.
Relative to so
Yeah, it's too weird.
It's like if the chair
So if it's like a particle,
But only three.
Here's what's going on here, by the way. What's going on here is, and here's at the bottom of this. The main thing is, if you're moving that way, the E field's changing, isn't it? Or if the charge moving that way. Well, if the charge is at rest, and you're moving relative to the charge, the E field's changing at your point due to the charge, isn't it? The thing that's important is, are you moving, you and the charge, are you moving relative to each other? Because if you are, there's going to be a B field produced by the E field changing.
Displacement changing.
It doesn't matter how it's happening, whether the charge at rest, you're moving, or the charge moving, you're at rest. The main thing is, are you moving relative to the charge? If you are, there's a B field from that charge.
So even if you're both moving, but you're moving slower than the charge, there's still a B field.
Yes, but if you're both going like this, there's no B field, is there? That's weird.
And then let's say you need to stop. So when you stop, the vehicle stops.
Yes. Well, no. But when you come to rest, then the B field is zero. After you come to rest. Why coming to rest is not because it's moving.
So there is a B field if you're walking, you're walking towards the.
Yeah, there would be a B field because and the reason why it's based on the E field changing. And the E field, if the charge at rest, you're moving relative to the charge, the E field of the charge at your point is changing, isn't it? It's getting stronger.
Just as if it was moving towards you.
Exactly. Whether you're doing this or you're moving relative to it, the E field's changing, isn't it? Where you're at, and that produces a B field. That's what's strange. All right, you didn't have to know that, but I thought it was interesting. All right. Now, to make sure that you have the direction right, let me give you some examples, okay? Because this takes a few examples. Let's do this. Let's say your moving charge is this way, and your point is this way. If the moving charge is right here moving that way, what's the B field is direction here due to that charge moving that way?
How do you do that?
Well, first of all, V is that way. What direction is little r?
Coming at you.
Little r is that way, isn't it?
So your B field is that way.
Let's check it out. Moving that way, scroll that way, B field's out of the page.
What?
Put your face direction of V, towards the little r.
No. Why is it? You're curling your finger. Why is it?
Go in, Brant.
Why is it this way, not like that?
Because you can do that, but how are you going to bend your face towards R with your hand turned that way?
You have to turn your hand.
You have to turn your hand so you can bend towards little
Switch
R.
your hands.
Yeah, and thumb's coming out when you do
Sounds
that.
like crooked.
My thumb's crooked, man. It won't work.
What's going on?
My thumb's like that, man. I can finish this if I just had the right thumb.
What do I do with my hand?
Everybody good?
So the little dot is the charge.
Huh?
The little dot is the charge.
Yes. No, the charge is here.
Oh.
We're trying to find the vehicle here due to that charge moving this way. And it's coming out because you point your face in the direction of V, going towards little r, which is that way, right? You curl it that way. If you're over here, you'd have curled it this way, right? And been that way. You follow me?
The B field's going.
That's just like any just point.
Well, the V field here is because I'm really going down here, right? My fingers up at V, curl towards your little r, thumb's coming out.
For an electron.
Because I got to curl this way, don't I? If I was flying over here, then little r would be that way, wouldn't it? I'd do V, curl towards little r,
And then
that
the
way.
problem little r is just going to be one.
Huh?
And then the problem little r is just going to be one.
Little r it's in the direction from where the point charge is to where the charge is at that time to where you're trying to find the B field.
Yeah, but like in the problem, mathematically, it's just going to be one.
Yeah, always.
Like no matter what, like
Yeah,
it would just be
it's 1 meter long in the direction of big R from here to here. Big R, that's little r. Big R means that whole thing there. Follow me?
Yeah.
And it's a vector, has a direction. Okay, good. Let's do, that's fairly simple. Let's do the problem. Now, they do I, J, and K stuff on this. The only time I do that is when you get to, what do I do?
IJK.
Yeah, just a second. There's one time when I do it that you need to, let's go up and determine it. When do I do it? Where is that? It's coming up, I know, and it has to do with magnetic field stuff. I'm not going to worry about it right now. But let's look at this, guys. On page 8, is it 884? I can't see. 884, let's do the problem down at the bottom there. And let's see. Noel, would you read that, please? 884, example 29.1.
A point charge of magnitude Q equals 4.5 nanocoulombs is moving with the speed of V equals 3.6 times 10 to the 7th meters per second parallel to the x-axis along the line y equals 3 meters. Find the magnetic field at the origin produced by this charge when the charge is at point x equals -4 meters, y equals 3 meters, as shown in figure 29-2.
Okay, now let's draw get the direction first and then get the amount, okay? All right. So we're right here. What direction are we going? Let's just redo a new one.
Right. To the right.
Going this way, V's that way. And you want to find the V field down here, don't you? I'm going to put right here. So, and okay, at the origin, correct? And you know from here to here is going to be, let me do this. How much is this 4?
Yeah.
It's 4, is it 4 meters? Yeah, I think it's 4 meters, right?
Yeah, no, it's.
Oh, yeah, but don't worry about that. Doesn't matter. I get what they're doing, but yeah.
4 meters.
Yeah, she would, but we're going to do the square root. We're going to do the Pythagorean anyway, so the negative doesn't matter, right? And this is 3. That's going to be 3. So right away, what's R going to be?
5.
Yeah, it's going to be 5. 4 3 5 triangle, right? 3 squared plus 4 squared, add them together, square root of 5. Okay. So this is going to be 5 meters right here. All right, but we got to get this angle here because that's the theta that matters, right? All right, now let's write everything out now we have that. Pull this up. I'm going to leave it there. Guys, I'm going to erase that a little bit so you can see your theta. All right. All right, so we're going to do this. The B field equals mu sub O over 4 pi times Q D, let's see, over, it's R squared, right? That's the non-vector form, right? Just the amount. All right, it's a plug and shove with that. Well, we got to get theta and then we're good to go, right? Okay. Do you want me to do all the givens and unknowns here?
No, it'll be all right.
All right, but what's theta, guys? We know it's going to be, if that's a 3, I can do 5, the cosine of that angle is going to be, we need the sine, right? 4 divided by 5, 0.80. Everybody clear? I did adjacent divided by, I need the sine? Dang. 3 divided by 5 is the sine, isn't it?
Yeah.
Opposite divided by the hypotenuse. Do I need to write, is everybody okay?
No, we can.
Okay.
Let's go.
So this thing, now I'm just going to cross it out and then put 0.60, right? 0.60, 3 divided by 5. Now let's fill in all the other stuff on this. Mu sub O, 4 pi.
So it's 60 degrees?
No, the sine is 0.60. I don't know what the degrees are. I don't care. I just need the sine. You with me?
Okay.
All right. And times, what did it say Q was? Yeah, let me do something real quick. I'm going to run out of room here. Okay. 4.5 times what?
4.5
Nano.
So,
All right. And what's the speed? How fast is it
6
going?
times 10 to the 7.
How much?
3.6 times 10 to
Okay,
the 7.
thanks. That is fast, by the way.
Yeah, that's all right. I can run that fast.
All right. And divided by R squared. Okay. Oh, 4 pi is over here.
What happened to the 4 pi that was under? Yeah.
Yeah. I'll put it right there.
Is there any way that would cancel out?
It will, yes. We're going to do that. And this is 5 squared here, right? All right. Plug it in so you can get the right answer. We should. Just cancel out your 4 pi. Now I get 615 times 10 minus 10. Man, I'm not getting their answer. What's going on here?
We just get one shot
Oh,
or something? Yeah.
Did I at least, did you get their answer?
Were you catching the 4 or 5?
No.
Yeah.
You just get one shot to the same 1 times 10 negative.
I should be getting their answer though. I may have plugged it in wrong. Let me check on my details. You got that right? We're good with that.
6.48 times 10 to the negative.
You got their, yeah, I'm not getting their answer, so let me check real quick.
What's their answer? Negative 3.89 times 10 to the negative 10.
Wait, what? I got a 6.48.
Yeah. But we're just playing what they have there, right?
Are we?
Yeah, look, I got the same thing on the board.
Yeah.
Let me check, see if I'm making a mistake.
That's what we get. Yeah, what is it?
Why are they getting a different answer? I don't know.
You didn't put the 0.6. Yeah, you left out the sign.
Oh, I did.
Yeah.
Times by 0.6, you get their answer, right? That's what it is. Yeah, let me check, make sure. That's what it is. That's exactly what it is.
Yeah, that's exactly.
Times by 0.6, you get their answer.
Yeah.
Everybody good?
No, you don't.
Yeah, you did.
That.
Yeah, we
We
got
got 3.89 to the 10. No, to the 7. And I'm not getting to the negative 10.
I am.
Next, the negative 10.
Yeah,
I
that's
don't
a
know
negative
what
9.
you
That's something weird.
It does come out right.
Yeah,
I didn't multiply it.
This guy got it. This guy got it.
Yeah, see, I just didn't multiply it.
See, I just put 10 to the negative 7. So that cancels out.
And here's the deal.
4.5 times 3.6.
Now, let's look at that. What direction is the V field here then? Oh, let's go back here. What direction is the V field do to that thing? Just do the right hand rule on it. V is that way. R is down, so throw that way, throw into the page, right?
Yeah.
Now, look at how they wrote this. They said a minus K, didn't they?
Yeah.
Because the minus K is unit vector. If this is positive K, the Z, the minus K is that way. Everybody got it?
Yeah, I got the wrong answer.
Wait. What?
In other words, this is Y, X, Z axis. You with me?
Yeah.
So in other words, we said the B field was that way. If this is positive Z, negative Z means negative K. K is the unit vector on the Z axis. Everybody good?
So,
Can I use XYZ? One thing is XYZ.
so for
Because they find it convenient in certain situations to do I, J, and K.
so we're using K for the Z, right?
Yeah. It's a unit vector.
Like having it all in English.
Now, you could just easily say so many Teslas in the minus Z direction. Same thing. All right. All right, guys, let's go on. Now, in what's called the, let's just do
Times the
this.
negative 7? Let's see the negative 7? No, it comes to the next one.
Guys, I'm going to do this. Put a minus here, K here, because that's the correct answer. Okay? It means in the minus Z direction.
That's why it's minus.
Yeah, because it's positive that way, minus is that way.
What's
All right. Now, the next thing, magnetic fields. Magnetic fields due to currents. This is called the Biot-Savart law. It must be some French guy. But it's found by a guy in Amper, so I don't know. Bless you, somebody.
Alright.
And it's this. Very similar to what you just did.
That's what you mean. That's what you
Real similar, isn't it? We're going to do two different applications. The third one's about solenoids. I'm not going to do it anymore. It's in the book.
derivatives?
No. Two applications, but I'm going to do two of the applications.
So
And they're easy to do.
This is current, and the other one's
The other one's for moving charge. This is for currents. Currents also produce B fields, okay? And let's see. So this is the same thing. Oh, this is the vector form, guys. So I'm going to do that. Non-vector would be this without direction.
Carry.
Where theta is angular. Other than that, you know what everything is. We'll do an easy application.
Eyes inertia?
Huh?
Eyes not inertia.
Do what?
What is that?
I.
Eyes current.
Oh, what's I?
Eyes is
Current.
yeah, that's what I said.
Thank you.
Yeah, I got you.
I know somebody said that, but I thought that the question was asked was not very intelligent.
Oh, have like big.
I'm sorry, Alonzo. It's not right, is it? Oh, did Daniel ask it?
Ow.
Yeah.
Turn it around. No.
Because I said it's due to currents, right? If I is in the equation, my guess is probably going to be current. You know what I'm saying?
Where are you going to get bold over there?
Daniel, you're the smart one. Come on.
Oh, don't worry. He'll pass the AP test, both of them.
He's like a nurse. I don't know.
All right, here we go.
What's eye?
Going to do a problem here, and
I never copy out there.
so we're going to do that. The B field.
This is what you're talking about, or you can do this?
Yeah. I believe so. The B field due to a current in a loop at the center loop. That's a Duke's way to state that, by the way.
Would it be kind of like a cylinder?
Like what? Yeah. If I understand you correctly, yes. Let's draw and then talk about the direction first, okay? Then we'll do the math. Let's do this. Here's what you're saying. It's in the book. And here we go.
That is exactly what I was asking yesterday.
Was it?
Yeah. About the semicircle?
Well, this is a circle.
The same thing, though?
Put two semicircles together.
Yeah, but the B field only acts at the center of the loop, right?
Yes.
That's what
So this is the same. Like, shut up, dude. I don't need you.
Oh God, third dimension.
That's good. All right, guys.